Welcome to video 4.1, Introduction to Momentum. We've been talking about motion for a while now and different things that affect the motion. And so we're going to continue with this unit to discuss not just kinematics or energy, but another aspect towards motion of objects. Momentum is the quantity of motion of a moving object. But what does that mean, the quantity of motion? Well, if you think about it for a minute, we actually talk about momentum quite a bit in our own lives. We think about, oh, it takes a lot to get that big truck moving, or, oh, that's not going to stop in time and it's going to hit the wall, or whatever. So when we're referring to motion, when we're referring to momentum, what we're really talking about is how difficult is it to start it, to stop it, or to change its direction, where the it is an object of some kind. To measure momentum, we have the equation that momentum is mass times velocity. So again, notice that I put the arrows over the P, the M, and the V, over the P and the V. This is because they are both vectors. Remember, they have direction with them. So P is momentum. Sometimes it's written as the Greek letter rho, but we'll use a P for it. We know that M is mass and V is the velocity. So we know, if we look at this from the units perspective, that mass is in kilograms and speed is in meters per second. So the units for momentum are the same. They are in kilogram meters per second. Let's look at an example of this to give you a better conceptual idea of what we're talking about. We have an elephant and a ladybug. Obviously, the elephant is considerably larger than the ladybug. So the question that I have for you is, which one has a larger momentum? Sort of a trick question, really, if you think about it, because momentum is mass times velocity. So if the elephant's speed is 0, then its momentum is 0. So if the ladybug's speed is even 1 meter per second, then its momentum is going to be greater than the momentum of the elephant, because the elephant's not moving anywhere. But what about if the elephant is out for their average stroll through the savannah? How fast are they going, and is there any way that a ladybug could have the same momentum or more momentum than the elephant? Let's take a look at some numbers to figure out if that is possible. The average mass of an elephant is 3,000 kilograms. The average speed of an elephant sauntering through the grasslands is 40 kilometers per hour. Well, we can't have speed in kilometers per hour. It needs to be in meters per second. So if we convert this, it's approximately 11 meters per second. So let's find out how much momentum does an elephant have. Well, 3,000 times 11, 33,000 kilogram meters per second. That's an awful lot of forward momentum that we have in this elephant as it's coming towards us, just sauntering towards us. I'm really not sure that we could even stop that, let alone a ladybug having that much momentum. So let's see, is there any way that a ladybug could have a greater momentum than an elephant if the elephant is going at least at its average pace? Well, in order to know that, we need to know the mass of the ladybug, and it is approximately 1 gram, which, if we change into kilograms, is 0.001 kilograms. So if we want the ladybug to have at least as much momentum as the elephant, 33,000 then would have to be equal to 0.001 times the speed of our ladybug. This is not looking good for our poor ladybug. The ladybug would have to have a speed of 3.3 times 10 to the 7th meters per second. That's almost the speed of light. That's craziness. So as soon as the elephant starts walking and getting to its average pace, there is no way that this poor ladybug can ever fly fast enough to have the same momentum, because the difference in their masses is just so enormous. Let's look a little bit more at momentum, the equation, and some more ideas about how we can solve these problems and what it really means to have that much momentum, or not to have that much momentum, depending on who you are. If the elephant is going to continue rambling around at the average speed of 40 kilometers per hour, he will have an average momentum. But if his speed does not change, does not stay the same rather, or his mass starts to change some because he picks something up, then we have to look at change in momentum. And for the change in momentum, the most common thing that happens is to have a change in velocity, an object speeding up or slowing down. You can have a mass change, so it could also be delta mv, but this is much rarer. You typically don't have objects that are losing parts of itself. You would if there was an explosion, of course, or if you had, say, you're driving down the car and you drop something out of the car, then the total momentum of the car would change because you've lost some mass. But for the most part, we tend to not worry about if a mass is changing, and most of the examples that we're going to be looking at are if the velocity is changing. Think back now for a minute to Newton's second law, F is equal to ma. That means that there has to be an acceleration. Well, an acceleration is a change in velocity. It's a rate change of velocity. So if we keep that in mind, that acceleration is a change in velocity over time, then F is equal to m delta v over delta t. The top of this now should look familiar. Force then is equal to momentum over change in time. We typically don't leave it written like this, although we can certainly use this formula. However, oftentimes the question is not so much how much force are we applying to change the speed of the object or to change the momentum, but how large a force and over what amount of time does the force have to be applied. So typically we are most interested in F equals delta t, which is our changing momentum. This equation right here, F delta t equals delta p, is often written as F delta t is equal to m delta v. This is another closely related topic to momentum, and F delta p is called the impulse. So if you change momentum, you're probably going to be changing speed. If you're changing speed, that means you're applying a force. You can either apply a big force over a short period of time to get a particular change in momentum, or you can apply a smaller force over a longer period of time to get the same change in momentum. And this is really important because if you think about it for a minute, let's say that we are driving in a car and suddenly a deer jumps out in front of us. If that's the case, then we want our momentum to change very quickly. We need a large force in a short period of time. So we slam on the brakes. Newton's first law says things in motion tend to stay in motion, things at rest tend to stay at rest unless acted upon by an outside force. If we have our seatbelt on, our seatbelt becomes that outside force and it slams us back into the seat. If we don't have our seatbelt on, then that outside force is not applied to us, our body, so we keep going forward with as much momentum as we have had previous to the brakes being slammed on. If we're driving down the road and we see at the top of a hill in a fair distance in front of us that there's a deer in the road, then we can apply the force to the car in a much longer period of time. We don't have to slam on the brakes. We're going to put the brakes on more slowly. So we increase the time, which means we can decrease the force for the same results. We will stop before we end up hitting the deer. So when we're talking about impulse and F delta t is equal to m delta v, we want to keep in mind that if we have a large force, we'll need a little bit of time to get a change in momentum. If we want the change in momentum to stay the same, we can also apply a smaller force over a larger period of time, and it will still have the same results. It's important to keep this in mind, not only because it affects our everyday life, but because keeping the difference between them clear is going to help you solve some problems. In fact, let's go ahead and take a look at a problem and figure out what we can do with this information about impulse and momentum. A car is traveling at 60 kilometers per hour. It slows to a stop in 12 seconds or 30 seconds. What force is required to stop the car in each? Okay, so let's take a look. If we know that we're looking for force, m delta v is equal to F delta t. So F is equal to m delta v over delta t. All right, so a car, well, the average car is about 1,000 kilograms. So for part A, we know the mass is 1,000. We know that the change of speed is going to go from 60 kilometers per hour to 0. We need to change kilometers per hour to meters per second. 60 kilometers per hour is about 16.7 meters per second. And we want this to occur in 12 seconds. This is the case where the deer is jumping out in front of you. So 1,000 times 16.7 divided by 12 tells us that the car brakes better be able to apply a force of 8.35 times 10 to the 6th newtons. That's a huge force. Let's see how much would occur if, rather than the time being 12 seconds, the time is now 30 seconds. So we still have 1,000 times 16.7, but now we're going to divide by 30. When we do this, it is 5.57 times 10 to the 5th newtons. So a considerably smaller amount of force is required if you more than double the stopping time. This is why when we jump up, we want to land with our knees bent, because if we land with our knees bent, then the muscles can absorb the shock of our weight coming down, and we can continue to bend our knees as we land. So we increase the time of the impact. So even though we have the same change in momentum, our time is greater, so the force on our knees is smaller. Airbags work this way as well, so that if you are in a car accident, even with a seatbelt on, you will tend to lean forward and you can hit yourself on the steering wheel. That's a hard object. The time of impact is going to be super tiny, so you can have a huge force hitting you. But if you have an airbag, then the airbag acts as a pillow. Even though it is still fairly hard, it acts as a pillow, so when you hit it going forward, you increase the time of impact, so the force decreases to the point where you're not going to die. Chances are you're not going to have major internal injuries either. Let's look at what happens if we are conserving momentum, similar to how we conserved energy. Momentum is conserved in all collisions, which means that the total momentum before a collision has to be equal to the total momentum after the collision. And we have to make sure we get all of the momenta in there, and that we keep in mind the different signs because they have different directions. The velocities have different directions. So let's take an example of, let's say that we have a ball that has a mass of 0.75 kilograms. It's moving this way at a speed of 1 meter per second. And it collides smack center with another ball whose mass is 1.5 kilograms and whose original velocity is 0. The question is, what's going to happen? Well, after they collide, they do in fact bounce off of each other, and the larger, let's write down that they collide. The larger ball then gets a motion, gets a speed of 0.67 meters per second. And the smaller ball bounces off, but we don't know what happens to it. We don't know if it continues on going forward at a slower speed, if it goes backwards at a slower speed. So this is what we want to know. What is ball 1's final velocity? So to solve this, we have to set up a conservation of momentum equation similar to this guy up here. So we need an m1 v1 initial plus an m2 v2 initial, and that needs to equal an m1 v1 final plus an m2 v2 final. Well, we know that this is 0 because originally the second ball was not moving. So I'm looking for the final velocity of the first object, so I can rearrange this to be m1 v1 naught minus m2 v2 final all over m1, and that will give me v1 final. Plugging in numbers, 0.75 times 1 minus 1.5 times 0.67 divided by 0.75. Now notice that the velocity of the second ball final is still a positive because it's still going in the irregular initial direction of the first ball. This is v1 final. If we solve this, we find out that the final velocity of the first ball is a negative 0.34 meters per second. This negative means that it is actually going backwards. So it does in fact bounce back away from the large ball back to the way it came. Let's take a minute and look at this particular situation with these two balls and see what happens when we change some other factors that affect the momentum. We are at PhET again, looking at a collision simulation. We have our objects here. Let's change the mass of the first ball to be 0.75 kilograms. The mass of the second ball we had at 1.5 kilograms, that's fine. They arbitrarily chose them to be at places of 1 meter and 2 meters. That's fine as well. And so the velocity, initial velocity of 1 is 1 meter per second, of 2 is 0. So automatically you see the momentum is in fact 0.75 kilogram meters per second for ball 1. So let's play this and see what happens. Notice over here on the right we have a momenta graph showing that is talking about how much momentum these objects have and in what direction, as well as the total momentum here in pink. So let's press play. Comes in, it hits, goes back out the other side. Now let's take a look at the arrows. Number 1, it does in fact go back out the other side. Look at the final velocity of ball 1, a negative 0.33. We came up with a negative 0.34. It's probably an issue of rounding. And the first ball has a velocity of 0.67. Its momentum is now 1. The other ball's momentum is a negative 0.25. So 1 plus a negative 0.25 is 0.75, still the same total momentum as what we had to begin with. We can change this around a little bit. Let's reset this. Let's make it so that we increase the mass of the first object to 1, and everything else will stay the same. So it has more momentum now than it did before, and it has more mass than it did before. Look at the end result. It still bounces backwards, but not as fast as it did before. And notice now it had a total momentum of 1 to start with. And conservation of momentum, 1.2 with ball 2, and a negative 0.2 with ball 1. Now let's make them the same mass. and see what happens. They hit, the first one stops, and the second one continues going. So all of the momentum from the first one is transferred to the second one. Might be a little bit different than what you had expected. With this introduction to momentum and to the conservation of momentum and to impulse, you have 3 important ideas here that will be beneficial to you